Hello everyone, for today's speaker is Laurent Cantier from Czech Academy of Sciences. So Laurent is going to talk about the Fraïssé theory for cone semigroups. Thank you.
Okay, thanks for the introduction and giving me the opportunity to present some work here. And overall, thanks for the thematic program, which has been a really nice time so far. So today I want to speak about one of my recent work joined with Eduardo Giralta. And basically we're trying to see if we could implement some of the Fraïssé theory for this category of abstract Cuntz semigroups. So about Fraïssé theory, I'm fairly new to the topic, so I will try to reference things, but I might forget some reference or these kind of things. So the first point of the first aim of the talk is to briefly explain to you what is Fraïssé theory, and also probably most of you are not so familiar with Cuntz semigroups, so also make a small recap on this. And then yeah, then I will expose the theory we developed and give you some example of natural abstract Cuntz semigroup that arise as Fraïssé limits. So introduction on Fraïssé theory. So this theory was is kind of old, so to speak. So it was originally introduced by Roland Fraïssé in the 50s, so 54 exactly. And so the setting he introduced and developed this theory was in model theory. Which again, I'm no expert, so I will try not to spend too much time on this. But basically, I wanted to study the correspondence between, so on one hand, some class of finitely generated structures, and on the other hand, countable structures that are homogeneous in a certain sense. So I will get more into detail, but basically would mean that whenever you have two finitely generated substructures that are isomorphic, you can leave this isomorphism to the countable structure. Okay, so there are plenty of examples that I will get into detail. And so on this work, he managed to actually get kind of a two-way correspondence under some property that I will also explain. So here we deal with object and arrows in some sense, and so over time there have been several Fraïssé theories that have been modeled out after this one. So for example, in 2006 we have Irwin and Solecki kind of dualize this thing, develop a dual version, which is called projective Fraïssé theory. And this is mostly to apply to topological spaces. And now, instead of talking about inclusion and embeddings, we will be talking about surjections, right? So, and so I guess most recently, Yusuf Kubis in okay, maybe around 2012, and probably some other people. Try kind of to use category theory to wrap up those two things under the same umbrella, and maybe allow also for some weakening. So instead of looking at things that are really homogeneous, which is kind of strong to ask, you will not ask that the isomorphism between finitely generated structure lifts to an automorphism of the countable structure, but probably up to some epsilon that you can choose arbitrarily small. Okay, so use category theory to develop, and we can let's say series. Okay, so the main idea is that now we deal with categories. So whether we speak about embeddings or surjections, these are just arrows, right? And you can just switch them around, whether you want to study like a projective version or an injective version of it. So basically the setting we will be on is we have a small category of object and arrows, which will correspond somehow to those finitely generated structure in model theory. And we want to know if we are in a so usually these things will not be closed under inductive limits and these kind of things, or projective limits. And we want to know under what condition on the object and the arrows, which will be the analogous of these properties that Fraïssé exposed in the first place, can we find limit object, which will be unique, universal, in the sense that for any of those objects, there is an arrow from small object to the bigger one, and that is almost homogeneous. Okay, so the almost homogeneity, I will write it explicitly, but you can think of, if you give me an object in C and two, okay, so maybe this is D. So two D arrows to my limits, which I'll call L, alpha 1, alpha 2. Can I find an isomorphism here that make this thing approximately commute up to arbitrary epsilon? Okay, so this is the main thing we want to look at. And it appears that under some properties that your small category will satisfy, then you can actually find this object in a bigger category that is almost homogeneous. Okay, so this is the main thing. So maybe let me give you some example of Fraïssé limit that have appeared over time. So probably maybe the first one is to look at this guy. So the rational number is the Fraïssé limit of all finite linearly ordered sets. Okay. This is not trivial, but it's true. And for example, here you can see that there would be other candidates for the universality part, meaning that all those guys can be embedded into the natural number or the integers, but you will not get this homogeneity property. Okay. So if you want to actually get the homogeneity property, you have to get this completion somehow. So this is one example. Then the Rado graph, so it's the graph with countably many vertices. And if you give me two two vertices, there is a probability function that there is an edge connecting those two vertices. So you can construct it recursively. And this is the Fraïssé limit of all finite graphs. So these are Fraïssé limits really in the original sense of Fraïssé. Then we have some projective Fraïssé limits. So for example, the Cantor sets and the pseudo arc. So I will come back to those. Are projective Fraïssé limits. Of some class that I will detail later, because I will actually use them and show some things. And one of the main motivation of this project is that Fraïssé theory have appeared most lately in system algebra. So there are several results in system algebras. So I should probably try to name some references. So for example, we know that all UHF, the Jiangsu, the Jaslon-Razak are all Fraïssé limits. Of suitable classes that I will not detail, but this has been done by Ilias and some co-authors. That is Masumoto, no? Okay. Yeah, so sorry. I warned you that some references will not be good. And this might have been in 16. Yeah. So this is Gassemi. This is Vignati and Jasselon. So I don't know the date of this. This was last year. Gassemi also proved the strong self-absorption of the Jiangsu using Fraïssé technique. So this is a nice application. And also another result is that there exists a universal AF algebra. Let's call it A. And for any AF algebra, so probably separable B, then there is a surjection from this universal AF algebra onto B. Okay, so this has been done by Kubis and Gassemi in 2021. Okay. Right. So some examples, some motivation, and hopefully you get a rough idea of what we're trying to do. So I've been really vague on what are those properties, what are those, what does it mean to be homogeneous? Because in the literature, there have been really many different people from many different backgrounds and many different timeline also that have wrote Fraïssé theory related things, and definition are not always exactly the same. So I don't want to say false things, but what I will put more in detail is this categorical version of it. So yeah, probably I'll start here. Okay, so we will always deal with small categories. So I don't have any trouble with the fact that the home sets are actually sets. And we want to be able to measure like distance or a metric between two arrows, right? This is kind of crucial for this theory. So what is a Fraïssé category? So I start with C is a small category, which is metric enriched. So basically you just have to think about it that the home sets are equipped with a metric which is non-expensive. So the fact that it's non-expensive, it means that if I have two arrows, I can plug in the metric and I get a value, how far they are from one another. And if I pre-compose or post-compose with an arrow, this has to give me like a smaller metric than smaller values than the original one I have. Okay, so pre-compose or post-compose cannot expand the distance. But this is technical detail. Basically, you just have to remember that I have a way to compare two arrows in my category, and it works well with composition, obviously. So we say that C is a Fraïssé category. Okay, so Fraïssé has a double point, but it's kind of, I will just write with one. So if it satisfies the following. So these axioms are really modeled out from the original Fraïssé theorem. So the first one we want is this joint embedding property. So if you give me two objects in my category, there is a third object such that the two can embed into that object, meaning that there exists an arrow from A to C and from B to C. Okay, so there exists a C and arrows. Okay. I just tag that those arrows exist. I don't require nothing else. Then we have this near amalgamation property. So now if you give me two arrows and okay, with the same domain, A1, A2, B2, and you give me an epsilon, an arbitrary epsilon, I can kind of close out the diagram such that it approximately commutes. Okay, so I can find beta 1 from B1 to some C and beta 2 from B2 to C, such that so it's a weaker form of push out because this does not have to be universal, but basically you want to find those beta 1, beta 2, such that this approximately commute within epsilon. Okay, so when I say this, I mean that the distance of the composition of those two maps with the composition of those two maps has to be smaller than epsilon. Okay. And a third condition, which is, let's call it a separability condition. So in our case, for example, we will be always dealing with countable small categories. So this will automatically be satisfied. So it means that basically I have a countable number of objects, and the home sets also are countable sets. Okay.
Sorry, Laurent, in the second condition.
Yeah.
Alpha 1 and alpha 2, they go from.
Yeah, sorry. Yeah, it's this. It has to be the same. Yeah. Usually those diagrams are easier and more explicit than the writing, which is a bit. But thanks.
You don't allow zero maps. There's a zero.
No, yeah, exactly. So the whole point is you have to think of the arrows to always be embeddings. And when you do the projective version of it, then all the arrows would be reverse. So you would have arrow. So in here, if you reverse, it doesn't change. But for example, the join embedding property would be the join subjective property. So for any object, there exist 2 arrows and 2 distinct objects such that I can subject out. But yeah, so no, because otherwise, yeah, but I mean, the whole point of this thing is it's really fragile on the arrows you allowed in your category, and we will always, you have to picture them as being embeddings.
Why not just say
because I mean, sometimes, for example, for C-star algebra, it's not clear what you mean by embeddings, and sometimes, like, I mean, you really want to use category theory here. You don't want to, like, your category could be anything. So what does it mean to be an embedding? Like, for example, for abstract Cuntz semigroup, we have this notion of order embedding, which will be.
If zero maps make sense and you don't explicitly exclude them, then it seems to me that everything whole show is off.
Examples of categories that don't have zero maps.
Yeah, because otherwise, I guess your Fraïssé limit would be somehow. I mean, if it exists, would be trivial or something like that.
Want to give an interesting example?
What's interesting about our C-star algebras are Fraïssé category in this sense.
So the C-star algebraic example I wrote, it's an interesting question. It has been done in model theory so far, and the universal one has been done in category theory. So and actually not quite sure how good one theory is. So I mean, the definitions are always a bit tricky. Like, you need, like, when you look at a paper, you need to really stick to what the author means by Fraïssé class or Fraïssé category or these kind of things. But yeah. So I guess if you have the zero map, then everything kind of collapsed.
This graph is just kind of becomes, like, both conditions become kind of boring. Like, you can always map to zero.
Yeah, but I mean, then the way you construct the Fraïssé limit, probably your Fraïssé limit will not be something interesting. That's my point.
Yeah, but I just don't understand if you allow it, why you allow it.
Why do I allow what?
Well, if it's not interesting, why do you allow, why not exclude the non-interesting?
The same reason you allow the zero C-star algebra.
Well, but that's gonna throw a monkey wrench. In this case, that's gonna, the zero algebra is gonna throw a monkey wrench into it.
It is the Fraïssé category, but we don't care about that. It's trivial. So we're going to look at ones where the maps are like isometries or something.
Yeah, exactly.
We're going to look at examples where the maps are like isometries or something, because they'll be interesting.
Because then this homogeneity thing is like.
But why not say GB is an interesting small category?
Oh, because, all right, what's wrong? There's zero and integer. Boring.
Okay.
Sorry, what is the separability condition?
So you need to have like a countable dominating subcategory. So
It can be boring because it can't fail to trust this particular, right? You look at the least non-interesting, positive non-negative literature, that's so factually interesting. And if zeros were uninteresting, then for that reason would be the least one, therefore interesting.
yeah, so I mean, yeah. Anyway, so if you have such an interesting category, probably not the boring one. Okay, no, I need first like, so this would be one. So this is the Fraïssé category, and the Fraïssé sequence is the following. So And this Fraïssé sequence is the one that kind of, in an explicit manner, will give you your Fraïssé limits. Okay, so an inductive sequence is a Fraïssé sequence if it satisfies the following. So okay, so for any alpha from one of the object of my sequence to any other object in the category, and any arbitrary precision, there exists some beta from C to Sj. J is greater than 1, then this approximately commutes up to an epsilon. So it means every time I
Every j bigger than I, or?
no, there exists one, but you want to enter back in the sequence at further steps. I mean, if it's before, then you can just compose it with sigma. I mean, you can always assume that you will enter in the sequence again, like at some forward step. That's my point.
Right, so there exists a j and there exists a beta from C.
Yeah, I mean, there exists an arrow from here to there, so you have to, yeah. Okay. Can always take it greater than one than I, and beta from C to Sj, such that this commutes approximately. Okay. And so the theorem of Kubi's goes as follows. And if we say category admits a Fraïssé sequence, which is unique up to two-sided approximate intertwining. So I didn't define those, but basically it means that you have maps that goes from up and down from your two sequences, and such that any path you take up and down, they are getting closer and closer, and the limits are actually isomorphic. I mean, it has to be shown, but it is true. And universal and almost homogeneous. In a certain sense, that is quite technical to write, but the interesting thing is actually the corollary that actually states that if you now go into a slightly bigger category that admits actually inductive limits, because usually those interesting categories, they will not have zero maps and they will not have inductive limits. Inductive limits. Okay, so you have to go to a slightly bigger category, and actually you cannot go in a too big category, but just something that has inductive limits and some nice arrows, and your Fraïssé limits will be living there, and we can rewrite this almost homogeneous property. So okay, so if you give me a Fraïssé category, then it has a Fraïssé limit. Let's call it L. In some completed category, I'm being vague around this, but for those who know, you can just take the incompletion. So it means that the object will be all the inductive limits of all the sequence in C, and the maps comes from more or less one-sided approximate intertwinings. So you don't want too many objects or too many maps there, otherwise you might lose this almost homogeneity property.
Sequence, there's supposed to be a direct sequence of the sigma identity that's supposed to be composed properly.
Say again?
Are you assuming sigma ij equals to sigma ki is sigma?
Yeah. It's
So what is alpha in that diagram?
it's any map.
So is it part, so for,
You fix a map that from one of this guy to some other guy in the category, like any map.
so for any alpha and for any epsilon.
Yeah, you can find such a thing. So L is unique up to C bar isomorphism. L is universal in the sense that for any, actually it's also true for C bar, but for any object there, you always have an arrow from C to the limits. It's different. Okay. And L is almost homogeneous in the sense that for any two arrow from C to the limit and any epsilon, I can find an isomorphism of my limits such that this approximately commutes. There exists such that okay. So it's kind of this relaxed version of the fact that any isomorphism at level of small object will almost leave to, yeah.
I'm a little confused now in terms of the zero. So it seems like if you took C star algebras with like, say, isometries or something as your category, you ruled out zero there, and you would, that should be, if I'm following the definition correctly, an example of a prosaic category. And then if I throw in zero as well and take another category that's the same but with zero and all the maps from zero and to zero included, then that would also be a prosaic category. But now in the one with zero, the constant sequence zero seems like it should be a prosaic sequence.
Exactly. I mean,
But there was a prosaic sequence in the non-zero version too. And that should still be a prosaic sequence even if zero is floating around in the category.
yeah. I mean, you kind of had yeah.
Yeah, if you do this construction suggested, you take up in this definition two, you take C equals zero. Then for your original per se sequence, you will not be able to find beta. Because
Right,
because
someone else-
there's
yes, okay.
because if your sigma ij are all
Right.
isometries, for example, then and alpha is the zero map, then there's no way to find the beta, any j and any beta.
Gotcha, thank you.
I don't quite see what the rule of alpha is, a logical rule of alpha. Maybe that question has been asked.
It's part of the data.
There exists data.
For every alpha,
Yeah, it's one of the original. If you have any arrow that goes out of the sequence, you can come back to the sequence
Okay.
and such that this mostly it's like if you stayed in the sequence.
Well, so that's where you get the interplay.
Yeah, exactly. I mean, this is exactly where the intertwining is coming from. Okay, so yeah, not so much time left. So probably a brief introduction on abstract Cuntz semigroup. So, okay, basically, I want you to think about this object to be like they have both algebraic and topological flavor. So, a CU semigroup is a positively ordered monoid. So let's call it S, and you have an addition and an order. The order is positive, and it's equipped with an order theoretic topology. Based on some auxiliary relation that I will write like that. So I actually don't know if one should call it Wavy law or compact contain, but probably some people in the room have an idea about that. But mostly it's a binary relation such that it's included in the binary relation of the order, okay? And it's not reflexive. Okay, and so also it's entirely determined by the order in the first place. So that's why we don't actually write it in the properties and fully determine. And this topology makes S a sequentially complete space. Okay. Let's just call it complete and continuous. Okay, so I don't want to get too much in detail, but just memorize that you have kind of an order topology there that makes things nice, and probably examples are better to explain than the actual definition. So, for example, if you look at the open set of topological space, U is compactly contained in V exactly mean what it means. It means that you can stick a compact space in between those two. Okay. If you take R, let's call it R plus, and maybe you want to complete it so that it's a complete space. X will be your Y. It exactly means that X is strictly smaller than Y, and so on. Okay, so
What means that S is continuous?
it means that I can approximate any element of my semigroup by some increasing sequence with respect to the stronger notion of increasement, and that the suprema is giving me my element. Okay. So those are examples of this this relation and some example of Cuntz semigroups. So the most basic one is actually a neutral for this category is the natural number completed with an infinite point. You also have truncated version of those guys, so probably all the n first natural number together with an infinity, and every time you sum two guys that exceed n, you fall into the infinite. We also have lower semi-continuous function space. So if you take all the lower semi-continuous function from X into this completion of the natural number, this is also a CU semigroup. I mean, X has to be compact and metric. And the last example might just be the Cuntz semigroup of a sister algebra, which is taking all the positive element in the stabilization and quotient out by some equivalence relation, and you can put a sum and an order there, is also a Cuntz semigroup. Okay, so I'm going really late. Yeah, So you might actually see that we run into a first big problem is that this order topology makes it hard to say what it means to measure two arrows, right? Because we don't have like a topology per se, and there have been not so many things done in distance of CU morphism. But in regard to classification, whenever we were dealing with this kind of spaces, one could use the topology available on X to actually define a distance on the home sets between two arrows that were coming out of this kind of CU semigroup. And this was very useful, for example, in the classification of AI algebras, then followed by some generalization of these results for some ASH algebra. So not only to classify theta algebra, but in the first place to classify star homomorphism. I also did some work on putting a distance in the home set of CU semigroups, and for example, I developed an approximate intertwining, but just in some specific case. And so one of the main motivation of this work was not only to try to study Fraïssé theory, but also to actually like define a proper metric and a proper way to compare to CU morphism. Okay, so let me quickly go over this. So obviously, this comparison of morphism should use the topology we have available. And okay, so
Take a look at the examples you gave of some Fraïssé categories and point out, I'm not sure if I could point to the unique Fraïssé sequence.
it's not unique, it's unique up to two-sided approximate intertwining.
Well, okay.
Because basically, if you have two Fraïssé sequences, you can just go out of one and come back to it. And
Well, sure, but I was just leaving out the phrase, the follow-up phrase, unique up to. That's that in my books that's called uniqueness. But my question is that you're explaining that you're giving an explanation why it's hard to pick out a particular Fraïssé sequence. Is that right?
no, I'm explaining that for abstract.
I just wondered if you would mind pointing out a particular Fraïssé sequence.
In which one?
Well,
The ones up here.
I'm not even quite sure what the categories are.
I mean, as I said, like the only categorical approach of all these things is that one.
Sorry?
The only thing that is done in a categorical Fraïssé theory is this universal AF algebra, right?
But what is it in that one?
I'll do it for like an analog for semigroup if you
I mean,
let
that's
me.
not something you can do right off the bat.
No, I mean, I don't remember what maybe you do, but
What about this universal AF algebra? Can you say anything more about that?
yeah, I will.
Well, okay, but picture, no one knows what's going to happen to the beat. But is this a unit? Are you talking about uniform maps?
You need actually left invertible maps.
Sorry?
You need left invertible maps.
Yes, but
So you need embeddings that can be retracted.
Maps, do they have to be units? You want them to be units?
Probably, yeah.
No, well, okay. But,
I mean, it's not my work,
anyways,
so
in the say surjection, that's already quite strong. And I'm just wondering.
yeah, I'll do the analogous theorem for semigroup, and the proof is kind of modeled out after this one. So maybe.
But this is a very elementary statement. It doesn't require categories. So just say there's an AF algebra, separable AF algebra that maps on to all other Is that the statement?
Yeah, probably.
But what's that got to do with, I mean, I'm not quite sure why it's on the blackboard, is it a fresh, where's the fresh,
So you can
where's the fresh-
I mean, again, this will be done, but probably not now, but so this is a Fraser limit of some special class. It's not like all AF algebra. You cannot put all arrows and all finite dimensional. So you have to look at left invertible things.
Not quite sure what that means.
So it means that you have a retract somehow. So it's an injection
Between what?
between your object. So you have a class of finite dimensional sister algebra, right?
Special sequence of finite dimension.
No, you have all the finite dimensional sister algebra, and the maps between those two in your category are embeddings that you can retract. Okay.
So it's special maps between.
Exactly. You cannot take all the maps, otherwise it will not work. It's,
I'm not quite sure what retract means. How can one finite dimensional algebra retract on a larger one?
I mean, they not always do. Like you just take out some maps that are not satisfying these things.
What's the example where it happens?
Huh?
If it's a direct sum of two things, then the direct sum maps onto each individual one. But I can't think of any other example.
I mean, yeah.
Well, that's what you're allowing. Fine. But it's a statement got nothing to do with any technical definitions as far as I can see. There exists an AF algebra that maps onto your.
I mean, the way they prove it is using this Fraïssé business. So
Well, but forget about the proof. The statement was there seems to be completely if it's what looks to me to be the statement, and it's got nothing to do with Fraïssé anything. It's just a statement of the AF algebra.
I mean, it's a nice application, I guess.
Well, I think that you can ignore that and just look at it as a statement. And even for you've got,
I mean, you have to construct. You have to show that it exists, right?
well, yeah, but it also implies that there's a corresponding statement for the reach the groups too. It would be nice to.
Actually, they do. Yeah. So probably there is other way to get to this thing, but
Well, it's an equivalent statement.
yeah, then using the classification result. Yeah. Okay, so I'll try to be quick. So now what's the way to compare when we don't have this topology available from a space? So if you give me two CU morphism, I forgot to specify, but those will be monoid morphism that preserve suprema of the increasing sequence and this way below relation. And so the trick was to be able to compare those morphisms on special sets here. So if you give me a finite set of the domain, we say that alpha and beta are approximately the same on G if for all pair of elements in my finite set such that one is way below the other, then
It's not standard English.
compact containing. I don't know what's the,
I'll say so. I'll say
Okay.
what it is. Standard English would be well below.
okay,
Or far below.
okay, so far below. So you have both images of the far below one that are smaller than both images of the far above one, yeah? And so a remark to show that this is actually a suitable way to compare. If I have that alpha and beta approximately compare on all finite sets, this is equivalent that alpha and beta compare on all sets of two elements with one being way far below the other, and it's the same as those two things are equal, okay? So now you can actually define what it would mean to be one-sided and two-sided approximate intertwining between two inductive sequences. And you can show the following theorem that any two approximate intertwining gives rise to CU isomorphism between the limit. Okay. So this is really not obvious and kind of technical, but the point is that now we have a way to compare morphism, and we have also approximate intertwining that are available. So I will reuse this thing. So now C will be an interesting small category, which is contained in the abstract Cuntz semigroup category. And we kind of want to use these tools that we have at hand now to define analogous statements. So we will say that C is a Fraïssé category of Cuntz semigroup, if you wish. So we still have this joint embedding property, which was not dealing with any comparison of maps. And now, so if you give me two maps and you give me any finite set of the domain A, I can find two maps such that these approximately commute within the finite set, and some kind of separability condition that will always be satisfied if you have countable categories. And same, we define a Fraïssé sequence. So it will be a Fraïssé sequence such that for any map alpha and any finite set in Si, so alpha is going from Si to C, I can find this beta, I can find this J and this beta from C to J, such that this approximately commute on the finite set that I have here. And we can show exactly these similar things. So any Fraïssé, like Cuntz Fraïssé category will admit a Cuntz Fraïssé sequence in this sense, which will be unique up to two-sided approximate intertwining, which is this new thing I defined. And yeah, all of these stay more or less true. So uniqueness doesn't it change, universality also. And here it means that for any two arrows from one small object into the Fraïssé limits and any finite sets of my small objects, I can find this automorphism such that this approximately commute within G. Okay, so we really managed to mimic an analogous theory to the one of Kubiš, and so now I will just give you all the example without any proofs. I'm sorry, but time is running out. So theorem. So if you consider the category, so SP, whose object are, so it's one object category, and all the maps are given by multiplication by P, and P is a supernatural number. Then this is Fraïssé in our sense, and its limit is, so this would be all the K divided by some divisor of the supernatural number. So if you think of like an infinite one, it would be like the periodic numbers, and you have to add this soft element, okay? And actually, this is the
By things which are actors of P is the maps.
yeah. I mean,
Okay.
yeah, exactly.
not just multiplication by p.
Yeah. It could be like a divisor of this supernatural number. And this is actually the concrete semigroup of the corresponding UHF algebra. And okay, so this is one. Then the category SDM. So now the object are any what's called simplicial CU semigroup. So it means any finite copies of this CU semigroup. And I take where am I? Here. And I take retractable CU morphism. So it means basically that I have from S to T, it means that there exists a sigma such that this way is the identity. Okay, so it's the usual notion of retract. Then this is Fraïssé, and its limits big S has this property that if you give me any inductive limit of these guys, which are called dimension CU semigroup, or any dimension CU semigroup T, there exists a surjection from this universal dimension semigroup to T. Okay. I wish I could do the proof. It's not so hard, but it's nice. But yeah, I'll probably wrap it up. 3 more. So the category of so now it's the same object, all the finite copies of this semigroup with other embeddings such that the unit is being matched to the unit is Fraïssé, and its limit is the lower semi-continuous function over the Cantor space into the natural number completed. And we have another one, which is kind of analogous result. So if you give me the category of one object, which is the lower semi-continuous function over the interval, and you give me other embeddings that match 1 to 1, also is Fraïssé, and its limit is the lower semi-continuous function over the pseudo arc. Okay, and yeah, a couple more, and that will be it. Yeah, sorry, I had some sketch of proofs for these things, but yeah. Now the category E infinity, which is all of this truncated version of the completed natural number for n greater or equal than 1, and the morphisms, I think they are just order embedding, if I'm not mistaken. No, you take all non-zero CU morphism is Fraïssé, and its limits is just the semigroup of any simple purely infinity star algebra. And the last one is a similar one, but now I just take some of these guys. So this is En, Now I will just look at the one that are power of some n for a fixed n. And other embeddings. Then is Fraïssé and its limits is a CU semigroup, which is simple, not stably finite, not weakly purely infinite, and whose order is total. So we know it's not this one, and we actually don't know if it comes from a sister algebra, and that could be an interesting question. We actually have some idea when n is a prime number, what it should look like. It should be kind of a truncated version of this one, where you consider all the elements that are smaller than the one, but the which is compact, because there you have a one that is compact and a one that is soft. And yeah, we don't actually know if it comes from a sister algebra, and that would give a nice example of the sister algebra with interesting property. So yeah, I'm a bit over time, sorry, and I'll finish here.